Good morning everyone. In today's Chem Help video we're going to look at mass spectrometry. It's one of the instrumental analysis components of the Year 11 ATAR course. Instrumental analysis is a tricky thing. If you're at university doing a chemistry degree, this would be in your third year instrumental analysis unit. So we're not going to expect a huge amount of detail when it comes to how these machines work. What you do need to do is understand the basic operation, the basic parts, and how it all flows together in a logical sequence. So let's have a look at that with this context of the mass spectrometer. There are two different types of spectrometry in Year 11. There's the atomic absorption spectrometer and there's the mass spectrometer. So let's have a look at this one. So what is a mass spectrometer? It's not very exciting, is it? It's just a bland looking box. They change size, you can get big ones, small ones. They're quite expensive to operate and to buy, but from the outward appearance, it's not that exciting. What is it though? A mass spectrometer, and there are lots of different types, is an apparatus for measuring the masses of isotopes, molecules, and molecular fragments by ionizing them and determining their trajectories in an electric and magnetic field. So it's a testing device. We can pick up elements, we can pick up molecules. You watch CSI TV shows, they use mass spectrometers all the time to prove who committed the crime, things like that. We use it for testing. It's a wonderful machine. It tells us a lot. How it works? Well, we're going to go through that now. Now you might be asking the question, why don't we use it all the time? Why don't we use it for everything if it's so good? Well, the problem is it's very expensive. The machines themselves are very expensive to buy and their operating costs are quite high. So you're looking at anywhere from about $300 to $2,000 to run an experiment compared to other testing regimes and other testing equipment, which is a lot cheaper. So that's why we don't use it all the time. But when you need great sensitivity and a great range of results, so you're not sure what's in your sample, for example, a mass spectrometer can be fantastic. This diagram goes through the basics that you need to know. Mass spectrometers, no matter where they come from, have four basic components in terms of their operation. There's an ionization component, there's an acceleration component, there's a detection or deflection, component, and a detection component. And it travels through a curved path. What we're going to do in this video is go through each of these sections and talk a little bit about the detail that you would need for an exam at the Year 11 level. Okay, so stage one is ionization. That's the first thing that must happen. So we have our sample, usually in an aqueous form. It's been prepared through another technique. Those techniques we don't need to go into. But what happens is the atom or molecule is ionized by knocking off one or more electrons to give a positive ion. So what we want is positive ions, not negative ones, positive ions. Now that's true even for things that you normally wouldn't get a positive ion. Of course, metals make positive ions, we know that, cations, sodium, magnesium, gold, silver, but other things as well, like chlorine, fluorine, which we expect to normally form a negative ion. We hit it with this electron beam, we force electrons to jump off. Even for things like noble gases, argon, things like that, we knock electrons off. So we work on the ionization energy component, try knocking them off to get them positive. Positive ion is the basis of which these all work. Okay, continuing on. The particles that are in the sample, the ions and molecules, are bombarded with a stream of electrons. Some of the collisions are energetic enough to knock off one or more electrons out of the sample particles to make positive ions. So this is just a little bit more detail than what was on the previous slide. Most of the positive ions formed will carry a charge of +1. And for most of the time talking through this video, that's what we're going to assume, because it's much more difficult to remove further electrons from an already positive ion. Although within any mass spectrometer, you do get +2 ions, +3 ions. We take that into account in part of the detection process, but we're just going to look at the operation very simplistically for now, and that's that it's a +1 charge. Okay, so stage two, once we've got the ions created, we now need to accelerate them or push them through the chamber. So the ions are accelerated by passing through a positively charged plate so that they have the same kinetic energy. The ionization chamber itself is charged positively to push the ions out, and then it passes through these plates to speed them up to the same kinetic energy. This all occurs in a vacuum. So one of the things about mass spectrometers is that it needs to be maintained, and there's lots of issues with cost about maintaining it in vacuums. We don't want any other particles in there, because if there is another particle in there, there'll be a collision and it will stop the motion or deflect the motion of the particle, and that would be bad from a mass spectrometry perspective. So we have them operating in a vacuum. All of the ions are accelerated into a finely focused beam as they pass through a slit in the acceleration chamber and move into the rest of the instrument. Okay, so that's acceleration. Detection, or deflection, I should say. In a deflection component, the ions are deflected by a magnetic field. Now, these two things in yellow are really important. The lighter they are, the more they're deflected. Okay, so think of atoms like different types of balls that are pushed into a stream of air. If you have a stream of air going this way and you fire a ping pong ball into the stream of air, it'll be deflected a great deal. If you have a cricket ball into the same stream of air, it won't be deflected much at all. If you have a ball made of pure lead, very, very heavy like cannonball, and roll it into the stream of air, it won't be deflected at all. So the deflection is all about how light they are in comparison to the magnetic field. So the amount of deflection also depends on the number of positive charges in the ion. That's the other component. How many electrons were knocked off in the first stage. The more the ion is charged, the more it gets deflected through the magnetic field. Okay, so that's important as well. Okay, a couple of other things. Different ions are deflected by the magnetic field by different amounts. That's really important. That's how we separate. This is the whole basis of this machine. We separate materials on the basis of their deflection. The amount of deflection depends on the mass of the ion. And remember, in a particular ion, the majority of the mass is in the nucleus. Protons and neutrons. The electrons, which we knocked off, are like 1/1840th the mass of a proton. They're tiny. The mass is concentrated in the nucleus. So lighter ions are deflected more than heavier ones. And also, of course, I said this before, the charge on ions also affects the deflection, but we take that into account when we're doing detection. Those two factors are combined in what we call the mass charge ratio. And usually we give that mass charge ratio the symbol M on Z. Okay, so we work it out the same. All right. Finally, detection, the last stage. The beam of ions passing through the machine is detected electrically. Now, how is this done, you might say? Well, what happens is only one ion stream makes it through the machine because of the way the deflector works. So light ions are deflected too much and they hit the side of the machine. Heavy ions aren't deflected enough. That's why the curve is important. So as it comes around the curve in that diagram, only one stream makes it through. Heavy ones hit the top, light ones hit the bottom. And what happens is those ones, the ones that are too light or too heavy, where they hit the walls, they get electrons when they collide with the walls of the machine, and they eventually get pumped out by the vacuum. But only the beam that we're looking at passes through. When one of those ions in that ion stream hits the detector, its charge is neutralized by an electron jumping from the metal box that makes up the detector onto the ion. So it's formed back into a metal, an atom or molecule once more. That leaves a vacancy amongst the electrons in the middle of the box of the detector, and the electrons in the wire shuffle along to fill it up. That causes a flow of electrons, which is a current. All right, and we can amplify that and record it. The more electrons that are arriving at the metal box, the greater the current is. So what we do is we get a current that is, so the more collisions, the greater the current. The lower the collisions, the lower the current. So we can get a measurement from a detection point of view. So what we said was only one beam passes through into the detector. So that would tell us about one element. But we wonder about, what about all the other elements? Well, how do we detect the others with those other streams that we're hitting the sides of the detector, either too heavy or too light? Well, what we do is we can vary the magnetic field. All right, so the lighter ions are the most easily deflected. They have the smallest MZ value. So to bring them into the detector, we deflect them by less. So we turn the magnet down, moves the beams, and moves the lighter beam into the detector. For the heavier elements or molecules with a larger MZ, we dial the magnet up again and we move the beam. So basically we're steering the beams into the detector. So we can actually detect them all by varying the magnetic field. Now, this is the important bit. If we vary the magnetic field, you can bring each ion stream onto the detector to produce a current, which is proportional to the number of ions arriving in the stream. Now, the mass of each ion being detected is related to the size of the magnetic field used to bring it onto the detector. So that's how we relate it together. The machine can be calibrated to record the current, which is a measure of the number of ions, against the MZ directly. And we do that with a software program or computer. It gives us that computation that we need to do. And what we get is the spectrum at the end. The output from this chart recorder is usually simplified into a stick diagram. This shows the relative current produced by ions against the mass charge ratio. And for a sample of molybdenum that's put through a mass spectrometer, we might get something like this. We often get relative abundance on this side, and what we get is we get mass charge ratio and we get these sticks. All right. Now these show us clearly the abundance of each one. Remember, the more ions, the higher the current. The greater the stick. So this shows us, when we put the molybdenum sample in, that there are a number of different isotopes. Okay, so it's 1, 2, 3, 4, 5, 6, 7 isotopes. 98 is the most abundant isotope within this sample, and these are the other ones that we've got. These three are the lowest in abundance, but that's how we can identify isotopes of different substances. You might find spectra in which the vertical axis is labelled relative abundance or relative intensity. Both means the same thing. Whichever is used, the vertical scale is related to the current, as I previously said, in the chart recorder. So that's the number of ions arriving at the detector. The greater the current, the greater the size of the stick on the stick diagram. So that's the basics of mass spectrometry, and that's the level that you need to know for Year 11 chemistry. I hope that's been helpful for you. If you found this video helpful, you can click like and subscribe, and hopefully the next one will be helpful for you as well. All right, see you later.